Welcome back to Science Fantastic with Professor Michio Kaku. We profile the amazing, jaw-dropping scientific discoveries which are revolutionizing our world and touching our lives. And this hour, once again, it's open mic. That's right, it's open mic on Science Fantastic. Okay, let's move on now and take the first listener phone call.
Hello, my name is Jacob Hutchinson. My question for you is, I've read that if you fall into a black hole, you see the whole timeline of the universe flash before your eyes. Does that depend on the mass of you in the black hole, or is that a universal truth? Thank you.
Well, you ask a very interesting question, because many people have wondered what happens when you actually fall into a black hole. What do you see? What sensations do you have as you fall into a black hole? Well, with our telescopes, we can actually see stars, star clusters falling into a black hole. The black hole basically has lunch. Now, realize that light, ancient light, can be trapped orbiting around the black hole. And so as you enter a black hole, you'll encounter ancient light that has been trapped, caught, whipping around, orbiting around the black hole. So in some sense, when you fall into a black hole, you see the history of the black hole. When it was created, how it was formed. It's sort of like some people say when you have a near-death experience, you see your life displayed in front of you just as you are about to die. Well, in some sense, the same thing happens with a black hole, because a black hole has captured ancient light going all the way back to its original formation, and you see this when you go toward the black hole. Now, it's not very pleasant falling into a black hole. First of all, tidal forces, gravitational forces tugging on your toes, is different than the gravity forces tugging on your head, so you get stretched as a consequence, and that's called spaghettification. You literally become a noodle as you head toward a black hole, as tidal forces stretch your body until eventually your body disintegrates into atoms, and then the atoms themselves get ripped apart by gravity. Gravity rips apart the electrons from the protons, and so you are basically a bunch of gas molecules and subatomic particles as you enter the black hole. Now, if that isn't enough, time also slows down as you enter the black hole. Now, if you watch this suicide as you head toward a black hole, if you see this from a distance, so let's say you're in a rocket ship far, far away, watching this sad episode with a telescope, what do you see? Time slows down from your point of view. You see that it takes hundreds, thousands of years for that person to fall into a black hole, because the light from the black hole is what is called blue shifted. Frequencies change and time slows down. Now, if you are the unfortunate person to actually fall into the black hole, then it would only take a few seconds for you to fall into a black hole, depending upon where you started from. So from your point of view, you've already vanished into the black hole and perhaps are dead. But to someone far away watching this whole spectacle from a safe distance, you would see the person frozen in time, because time slows down as you head toward a black hole. In fact, I once read a science fiction story where the bad guy at the end of the novel falls into a black hole and he screams for 1,000 years. Okay, well, let's move on now and take the next listener phone call.
San Jose, California, Albert. 2001, A Space Odyssey, the movie, I'm sure you're well familiar with it. The computer, HAL 9000, do you think today they can make a machine just like HAL? And as far as consciousness that you always mentioned about robotics and machinery, I don't think it would be self-aware. It merely mimics the human mind, but at a phenomenal rate of speed. That's why it outwitted the crew of Discovery 1. I've done a lot of research on that. So what's your opinion? Is there a HAL 9000 today? Certainly not from Urbana, Illinois. And I just wanted your opinion. By the way, he was a Capricorn, too, by the way, if that helped anyone out. Thank you, Doctor.
Okay, well, first of all, yes, I've seen most of the great science fiction movies. I love going to the movies. When I was a kid, I would thrill at all the exploits of astronauts going into outer space. Today, however, I cringe a bit because being a professional physicist, I can see all the mistakes and errors that are made in the movie. However, you have to suspend your beliefs a little bit and just enjoy the show. I enjoy watching science fiction movies. And 2001, I think, is one of the most realistic movies, but I think they got the date wrong. Instead of being 2001, it should have been 2100. That is, I think he was off by about 100 years. 100 years from now, we may have regular manned journeys out to Jupiter and beyond. And perhaps by the end of this century, we'll have robots that are every bit as intelligent as us, and we can have intelligent conversations. Now, today we have Alexa and things like that are called chatbots. That is, they can talk to you, they can answer simple questions, but you can't engage them in gossip, you can't talk shop with them, you can't treat them as a friend. And that's where robots have failed. Robots are very good at things that are repetitive, things that don't require imagination or creativity, but they fail in 3 or 4 big areas. Listen carefully, because these are the areas where there are going to be jobs in the future. I repeat, the jobs of the future will be areas where robots cannot fill. One is human interactions. So, for example, in a law firm, the paralegal may be replaced because the paralegal is basically a search engine looking through law books. But the lawyer, him or herself, has to engage the jury, has to understand ethics and morals of society, which constantly change, have to argue to a judge and a jury. And so human interaction is one thing where robots are very deficient in. And this means that those jobs that require those skills will be around for quite a while. Next is pattern recognition. For example, our most advanced robots cannot fix your toilet. Things that are non-repetitive and require semi-skills cannot be done by robots. Robots cannot pick up garbage. They cannot solve a crime like what policemen can do. They cannot build a house like a carpenter. And they cannot make a garden like a gardener. But things that are repetitive, that's where robots can excel. So pattern recognition is another area that robots do not do very well at all. And then there's common sense. We know that water is wet, not dry. We know that mothers are older than their daughters. But how do you know that? How do you know that strings can pull and strings cannot push? Well, that's common sense. Any idiot does that, right? Well, yeah, any idiot except robots. Robots do not know that water is wet because they never encountered water and wetness. I mean, why can't water be dry? And mothers are older than their daughters? Well, according to Einstein, that's not necessarily true. But for the most part, mothers are older than their daughters, but robots don't know that. And so jobs involving common sense will also be off the table for quite a while. And then jobs that require imagination, originality, innovation. Those are jobs that robots cannot perform well at all. So intellectual capital is going to be the currency of the future, not commodity capital like agriculture, making metals and different kinds of commodities, but intellectual capital, the capital of the mind, making jokes, creating new scientific theories, becoming a teacher and a mentor. These are things that require human skills, and that's where robots are lacking. And maybe in 2100, that movie, 2001, will in fact become very close to reality. Okay, let's move on to the next listener phone call.
Hello, Doctor. My name is John Cloud, and I'm calling from Pasco, Washington. The call letters of the radio station is KONA AM 610. I am wondering about a product that has been around surfacing here in the United States called TriboTex. It's they say smart nanoparticles. It goes inside of a gas and diesel engine. I want to know how safe that is and if that's a gimmick or what. nanoparticles that say superlubricity. Could you please explain what that is? Thank you.
Well, there's a lot of hype around nanotechnology, which is the technology of individual atoms. And in the future, one day, perhaps we'll have atomic machines that are the size of atoms, atomic levers and gears and hammers, and that could create, of course, a new industrial revolution at the atomic scale. But where are we today with this technology? The promise is you could become a magician like Harry Potter. You wave your magic wand and a rabbit comes out of your hat because you rearranged atom for atom the molecules in that hat. We are far away from the promise of nanotechnology. So where are we with nanotechnology? One is lubricants. That is layers of surface with, let's say, carbon and carbon composites and graphene that can form layers on materials to give them strength, to make them slippery. And so that's one area where there is an industrial application, is in micro lubrication. Also, graphene, I mentioned. Graphene is a single layer of carbon. And as a consequence, scientists have been able to make transistors out of a single carbon atom, which will eventually give us molecular transistors. I mean, think about that. Instead of those clumsy silicon transistors that you find on your PC or your cell phone, we'll have transistors the size of carbon atoms, and that could give us a new industrial revolution. Now, there is some controversy, as you pointed out, and that is safety. At the present time, the safety tests on many of these chemicals have not been thoroughly done. And so we assume, for the most part, that these industrial lubricants are not going to be harmful. But, hey, you never know. It's one of these things that still have to be tested. So for the chemical you mentioned, I'm not sure, I'm not familiar with that specific chemical, but you have to be careful because lubricants have been used, microlubricants made out of nanotechnology, but you have to worry about how safe they are and whether or not, for example, the FDA has given any guidelines. But this is a frontier area. Another area where nanoparticles are very useful is medicine. It turns out that you can create nanoparticles that home in on individual cancer cells, killing them one by one. That is astounding. And some people think that's the future of cancer research, knocking out cancer cells one by one. One way to do that is to modify your immune system. This is called immunotherapy, so that it recognizes cancer cells and kills them. Another is to artificially create nanoparticles, which also zoom in on cancer cells and knock them out one by one. All this, of course, is still at the cutting edge, but one day nanomedicine can really turn ordinary medicine upside down. Welcome back to Science Fantastic with Professor Michio Kaku. In this hour, once again, we're going to throw the lines open because it's open mic on Science Fantastic. Let's move on now to the next listener phone call.
Hi, I'm Andrew Rosick, calling from Richmond, Michigan, and I had a question for you about light waves, and I was wondering if a wave of light was a dimensionless phenomena or had dimensions that can be explained. Thanks, Barry.
Well, you ask a very intriguing question that has dogged science for centuries. Light does seem to be different from other objects. For example, if you take an object and you boost it, you have to, kick it or put a rocket on it, and it takes time. It takes time for an object to build up speed, and it's a question of inertia. So objects have inertia or resistance to change. Light, on the other hand, you turn on the light switch and bingo! It immediately races at the speed of light. No warming up. No getting up to speed. It immediately goes at the speed of light. And so you say to yourself, well, light really is different from other kinds of matter. is really quite different. And the reason is the mass of the light beam is zero. Not that it doesn't have zero dimension, it has zero mass. Therefore, it takes no effort to simply turn on a flashlight and boom, it goes to the speed of light. No warming up, no revving of your engines, none of that. Immediately, it goes to the speed of light because the mass, the rest mass of light is zero. Now, some people say, now, wait a minute. Einstein said E equals mc squared. Energy is mass times c squared. M appears in that equation. So doesn't light have mass? And the answer is no. You see, E equals mc squared is actually a truncated equation. It's not the complete equation at all. The complete equation is quite different. And for light, it is energy is equal to momentum times the speed of light. And so momentum can even exist with zero mass. And so you see, the equations for light really are different from the equations for ordinary matter. But we know E equals mc squared. We don't know the equation for light because, unfortunately, they don't teach it in elementary school, even though they teach E equals mc squared. Now, does light have dimensions? And the answer is yes. In fact, it is a wave. You can graph it on a sheet of paper. In fact, it was James Clerk Maxwell, 150 years ago, who first discovered what light really is. If you get a magnetic field, for example, and you vibrate it, it creates an electric field. A vibrating electric field creates a magnetic field. That's how motors work. That's how your bicycle lamp works. Anytime something spins or moves, it creates an electric field and a magnetic field. Well, Maxwell then got a sheet of paper and drew this curve. You get a wave, one wave creating the next wave, creating the next wave. And then he asked the key question, a question which really changed human history. What happens if electricity turns into magnetism, turns into electricity, turns into magnetism, and it goes back and forth, and it creates a wave of electricity and magnetism. Well, let's take a short commercial break, and after the break, I'll answer the question, what is light? And how did Maxwell figure out what light is? Welcome back to Science Fantastic with Professor Michio Kaku. And before the break, we had a question about the nature of light. And then the question is, what is light anyway? It seems to be so different from ordinary matter. Well, that was actually figured out 150 years ago by the British physicist James Clerk Maxwell. We know about electric fields. For example, electric fields make your hair stand on end if you get charged up. It's the spark you feel by walking across the carpet. It's the electricity you get from the wall. And it's the electricity you get in a lightning bolt. All these are due to electric fields. Then we have magnetic fields, like the magnetic field of the Earth, which makes compass needles point in the direction of north. And then you have dynamos and motors. How do they work? Electric fields turn into magnetic fields, which turn into electric fields. So, Maxwell said, if I have an electric field, and it turns into a magnetic field, like a ping pong, it goes back and forth, it creates a wave. And then he said to himself, well, that's nice. If vibrating electric and magnetic fields create waves, then what is the velocity of this wave? Well, it's a very simple calculation. He calculated the speed of the wave, and then he practically fell off the floor. He made one of the greatest discoveries in the history of the human race. He discovered that the velocity of a wave created by electricity turning into magnetism, turning into electricity, the velocity of that wave is the speed of light. And then he said, I paraphrase, he said the most momentous words of the electric age. He said, this is light. Light is an electromagnetic field. It's a field created by electricity turning into magnetism, turning into electricity, vibrating back and forth like a ping pong ball, traveling at a velocity, and that velocity is the speed of light. And then Maxwell said, this is light. one of the greatest discoveries in the history of the human race. And then Einstein, a century later, actually about 40 years later, took these equations of Maxwell and finished it. Unfortunately, Maxwell died when he was 40-something years old, and he was not able to complete his theory. Einstein took Maxwell's theory and said, "Ha! This is just the beginning. That is, if this is light, then let's calculate the speed of light as you go in any direction." And then Einstein realized that the light beam traveled at the speed of light no matter how you looked at it. And then he came up with the theory of relativity. And so what is light? Light is an electromagnetic field. Electric fields turning into magnetic fields, turning into electric fields, traveling at a velocity, the velocity of light itself. Okay, let's move on now to the next listener phone call.
Hi, my name is Shane Thompson. I'm currently in Fountain Valley, California. My question for Michio Kaku is, what are your thoughts on the grand solar minimum? The way the sun seems to have an effect on our weather here on Earth and it's causing climate change. Thank you.
Okay, yes, if you take a look at the sun and graph the sun's output over a long period of time, you realize that it's not steady. You begin to realize that there are fluctuations in the sun. And, for example, years ago, the sun's intensity was different than it is today. And if you look at the history of stars in the heavens, there are so many stars in the heavens that you can see stars in any phase of their life, from birth to maturation to eventually they die or they undergo supernova. You can see stars at any phase of their existence. And so with stars, we can then compare the life history of thousands of stars to the life history of the planet Earth. And you see that, yes, it turns out there are cycles, that there are areas where light can diminish or expand. However, I'm not so much worried about that. I'm worried about when the sun has a temper tantrum, that it erupts with the fury of a solar flare. Let's take a short commercial break, and after that break, I'll talk about what happens when all hell breaks loose, when the sun unleashes a temper tantrum and creates what is called the Carrington event, which can really ruin your day. Welcome back to Science Fantastic with Professor Michio Kaku. Before the break, we had a question about the sun. Yes, the sun does have cycles. Yes, the sun's intensity can increase or decrease. But does that cause global warming? No, it is not sufficient to influence the weather that much, especially because the weather has been changing over the last 100 years. And many of these cycles take place over a period of thousands of years. However, there's one kind of event that really does worry climatologists. And that is a gigantic solar flare like the Carrington event of 1859. It was a gigantic explosion on the sun as a solar flare went hurtling from the sun and hit the Earth. And it was seen by the astronomer Carrington. That's why it's called the Carrington event. And it influenced telegraph wires back in 1859. Now, we physicists today, knowing the intensity of what it takes to disturb telegraph wires, can then now extrapolate to what it would be like today if a Carrington event were to erupt today. And it's not going to be very pretty. Property damage would be on the order of $2 trillion. That's trillion with a T, not a B. It means that power plants would be short-circuited, satellites would be fried, telecommunications will be disrupted, the internet will go down, your power in your house would go out as the power supply is short-circuited, credit cards cannot be taken because, of course, everything's offline, and it means that refrigerators are all going to go on the blink because there's no power, which means food riots in the next few days. It's going to be a real mess. And so we physicists, knowing this, went to Congress and said we need a few $1 million in order to reinforce our satellites, reinforce our power plants, build redundant systems as a safety precaution. And all we get was Snickers. Snickers from Congress. So much for alerting our wise lawmakers about a real potential catastrophe when the sun erupts in the fury of a gigantic coronal mass discharge like what we had before. Now, how often are they? We don't know. Perhaps on a scale of hundreds of years, we don't know. We've only had one, and working backwards, we've been able to work out the dynamics of that solar flare and exactly how intense was the electric field. For example, we know that as you travel north, you get the aurora borealis because of the solar wind which hits the North Pole. However, during the Carrington event of 1859, as far away as Cuba, they saw the Northern Lights. The Northern Lights not in Finland or Sweden. No, the Northern Lights in Cuba. That's how massive this solar flare was. And as I mentioned, we physicists can then reverse engineer that to calculate the intensity of that solar flare. And it was humongous. It was off scale, meaning that every few hundred years, a whopper is going to happen. And remember back in 1859, what did we have? Did we have television? Did we have the internet, iPods, iPads? No. We had Morse code and telegraph wires. That's all we had back in 1859. Think of what that would do today to our power plants, to the satellites, the internet, telecommunications, telephones. It would be a real mess. Okay, let's move on now to the next listener phone call.
Hi, Dr. Kaku. My name is Eddie. I live in Ogden, Utah. I just listened to it on YouTube, rather. I had a couple questions that maybe you could clarify. I think that your listeners would really be interested in is, can you explain what frame dragging is, as well as the tachyon anti-telephone paradox? Thank you. Love your show.
Okay, frame dragging is a consequence of Einstein's theory of general relativity, where space and time have a life of their own. They are a fabric which can bend and stretch, and that gives us the appearance of gravity. So the pulling and tugging of gravity is actually the pulling and tugging and stretching of space. Now, as a black hole rotates, it's like molasses rotating, and if you are, let's say, a bug floating in molasses, you are dragged along with the molasses as it spins. That's called frame dragging. So frame dragging is when you have, for example, a black hole, and you're caught up in the wake of the spin, and you are then dragged along with the frame being space and time. So that's how that works. And we actually see frame dragging. This was, of course, a consequence of Einstein's theory of 1915, but we actually see evidence of this as we see entire star systems and gas clouds suck right into black holes as they have their lunch. And then tachyons. Well, first of all, let me explain what a tachyon is. A tachyon is a hypothetical particle that goes faster than the speed of light. And if it goes faster than the speed of light, then in some sense it gives you a form of time travel. That's why we physicists are very skeptical about the existence of tachyons. Of course, on Star Trek, tachyons are a preferred way of communicating because it would allow you to communicate faster than the speed of light. However, don't believe it. We have seen no evidence of tachyons. Maybe a tachyon destabilized the Big Bang at the beginning of time, but that's about it. So far, we see no evidence of tachyons. Well, unfortunately, that's it for Science Fantastic. Good day. Welcome back to Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries which are revolutionizing our world and touching our lives. And this hour is your hour. So let's move right on to the first listener phone call.
Hello, I have a question about all the satellites that no longer work, and we're trying to figure out a way to get rid of them. I hear things about grappling hooks and nets and things. My question was about magnets. Couldn't we launch a good-sized magnet satellite out there to collect all the little broken satellites, and eventually it will become heavier and heavier, pulling it towards the Earth's atmosphere in order to burn up? The weight will actually pull it towards the atmosphere as it collects the satellites. Just a random question from an average Joe. Thanks. My name is Tim, and I'm from Buffalo. Thank you.
Well, Tim, you ask a very embarrassing question because we humans have littered outer space with our junk. You realize that there are thousands, literally thousands of pieces of space junk orbiting the planet Earth, whizzing around the Earth at 18,000 miles per hour, created by all the missiles that we have launched into space. Every time we send something into space, we put up booster rockets, screws, screwdrivers, gloves, all sorts of nonsense is shot into outer space every time we send our astronauts up to the International Space Station. In fact, NORAD and our military tracks these things. We have a special computer program that is specifically designed to keep track of all these space debris. Now, what do we do with all this space junk? Well, the short answer is we don't know. At the present time, there are no active experiments being done to get rid of the space junk. However, that hasn't stopped people from trying to field some ideas. Now, your idea of magnetism sounds attractive, but there are problems, practical problems, because first of all, magnetism does not extend very far. And we're talking about objects whizzing around the Earth at 18,000 miles per hour that may be separated by hundreds of miles, over which magnetism simply will not work. Second of all, electromagnets require lots of electrical energy, and energy is at a premium in outer space, and that's yet another reason to believe that magnets simply won't cut it. So magnets are simply too weak. They're not long range, and they simply don't have the ability to snag all the junk that's out there, all the way from paint flecks to screws to gloves, all the way to booster rocket parts. Now, one idea that I found going through the internet, a proposal that would use a net. It would have retro rockets that would allow them to maneuver between pieces of junk. It would then snag the junk with a net and then go to the next piece of junk. And after that, it would simply dive back into the atmosphere and burn up. So there's no necessity to bring it back to the surface of the Earth. It would simply burn up like a meteor in outer space. But, well, if you can figure out a better way to do it, call a press conference. Call the military. Because at the present time, we are clueless as to what to do with an economical, practical way to get rid of all the space junk. And it's going to be a very big problem for our astronauts as they move on to the moon and Mars. Okay, moving right along now, let's take the next listener phone call.
Yes, Dr. Kaku. My name is Chris Duffy. I'm from Washington, D.C. I have a question about gravitational waves. I'm a little confused as to its nature. Does it behave like light and it's its own independent waving entity like electromagnetism? Or is it like a water wave where what is waving is actually a substance or a medium, and that substance medium being space-time? I've had a heated debate, and I can't find a satisfactory answer, so I would appreciate one. Thank you very much.
Okay, well, the answer is very simple. First of all, let me say that 3 colleagues of mine won the Nobel Prize in Physics for the discovery of these gravity waves emanating from colliding black holes in outer space. Who would have thought that we would have instruments sensitive enough to detect emissions from the collision of 2 black holes a billion light years from the planet Earth? So it took 1 billion years for that cosmic radiation, gravity waves from colliding black holes to actually hit the planet Earth. Well, according to Einstein, space and time are like a fabric that can be stretched, also a fabric that ripples. So think of throwing a pebble into a pond. When you throw a pebble into the pond, you get water waves that emanate from the center of the impact. Well, that pond is similar to space-time, and the ripples on the fabric of space-time are gravity waves. And how fast do they move? At the speed of light. And so these gravity waves are different from light waves. And this will initiate a whole new era of telescopes. Realize that the first set of telescopes used light going all the way back to Galileo 400 years ago. That was the first generation of telescopes. The second generation of telescopes dates back to World War II, when we used radio waves, and we detected radio waves from galaxies in outer space. And now we're entering the third era, when we're not using light, we're not using radio, but we're using ripples in the fabric of space-time itself. Gravity waves that were predicted by Albert Einstein in 1916. Think about that. About 100 years ago, Einstein predicted that if space and time were like a fabric, ripples on that fabric should travel at the speed of light. But he thought that these ripples are so faint they would not be discovered in his lifetime. And he was right. It took 100 years since his prediction to actually find these things. Next, we're going to go into outer space and have gravity wave detectors in outer space detecting radiation from the instant of creation itself. We're now talking about baby pictures, getting baby pictures of the instant of creation when the infant universe emerges from the womb. And many people think that gravity waves will give us a snapshot of the infant universe with an umbilical cord. An umbilical cord connecting our baby universe to a parent universe in a multiverse of universes. Well, that, of course, is still beyond our capability. But the next step with gravity waves is to put detectors in outer space to get photographs of the infant universe as it was created. Okay, let's move right along now to the next listener phone call.
Hello, my name is Adam. I'm from Manhattan, and my question is, do you see human civilization within the next, let's say, 50 years becoming completely self-sustainable, or a type 1 civilization? Thank you.
Well, let's break down the terminology. First of all, when we physicists analyze intelligent life in outer space, we don't look for little green men. We rank them numerically by energy. A Type 1 civilization has harnessed the energy of an entire planet. They are a planetary civilization, somewhat similar to what you see in Flash Gordon or Buck Rogers. They control the weather. They would control earthquakes and volcanoes. Anything terrestrial, they would control. Type 2 is stellar. They control the entire energy output of a star, and they would, for example, perhaps even envelop their entire star with a sphere called a Dyson sphere to extract energy from their sun. They play with stars. An example of a Type 2 civilization would be Star Trek. The Federation of Planets would be a typical Type 2 civilization. Then there's Type 3, galactic. They roam the galactic space lanes, zipping from one star system effortlessly across the galaxy itself. And that's somewhat similar to what you find in Star Wars, where you have a galactic civilization. Now, what are we on this cosmic scale? Do we play with the weather? Can we juggle stars? Can we roam the galactic space lanes? No, we are Type 0. We get our energy from dead plants, oil and coal. And I would suspect that in 100 years, about 100 years, we will become a Type 1 civilization, truly planetary. Not 50 years, but perhaps in 100 years. And you see the beginnings of it right now. For example, what is the Internet? The Internet is the emergence of the first Type 1 planetary telephone system. Think about it. The Internet is a Type 1 technology, truly planetary. And you can see remnants of this in culture as well. For example, what is soccer? What is the Olympics? The beginning of a Type 1 sports. What is the European Union? Well, the beginning of a Type 1 economy. What is the Type 1 language that these people will speak? Probably English, because if you go to the Internet, the number one language on the Internet is English, followed by Mandarin Chinese. And even a Type 1 music is emerging. We have rock and roll and rap. A Type 1 culture is emerging in high fashion. Take a look at Gucci or Chanel. We find those luxury brands anywhere on the planet Earth. Now, the caller asked, will we become truly self-sustaining? Well, in 100 years, I think so. But even before that, there are good indications that we will become self-sustaining. First of all, the electric battery. People wonder, why don't we have the solar age or the wind age? All the propaganda from Hollywood about solar power never came to be. Well, the problem with solar power is not the solar cell at all. It is the battery. The lowly battery storage is the number one problem because, of course, what do you do when the sun doesn't shine or the winds don't blow? You need batteries. And that's been the weak spot. The weak spot toward a totally self-sustaining civilization. But the price of batteries has been dropping about 7% a year as inventors and entrepreneurs jump on the bandwagon to create the super battery of the future. Then after that, I would expect fusion power to become a reality. Within the next 15, 20 years or so in southern France, the ITER fusion reactor, costing about $12 billion, will generate more energy than it consumes, and we could be entering the fusion era. Fusion is the power of the sun. Literally the power of the sun on the planet Earth. And so I think we will become self-sustaining, not anytime soon, but within the next decade or so, solar and wind are going to be playing catch-up to fossil fuels, and beyond that, we could be entering the fusion era. Okay, well, let's move right along now to the next listener phone call.
Hi, my name is Tag Ryan. I'm from Omaha, Nebraska, and my question is, what sci-fi fantasy world is most technologically plausible? Thank you for your time.
Well, you ask a tall question. First of all, I'm a science fiction fan. I cringe sometimes when I see movies where all the physics and the science is upside down, backwards, and unrecognizable. However, I love to watch the special effects. I would say that perhaps the most scientifically valid movie is, 2001. Because in that movie, we're talking about a civilization on the moon. You see, if you are a galactic civilization, it would take simply too long to explore the entire galaxy. The galaxy is about 100,000 light years across, so it would take 100,000 years traveling at the speed of light to go from one end to the other. That's simply too long. So what they would do is they would send robots, self-replicating robots that can have children, and they would land on the moon. Now, why a moon? Because the moon has no erosion, there's no rust, and as a consequence, any probe on a moon would stay there for millions, billions of years, and all it would do is make a copy itself. Not one copy, but maybe 1,000 copies of itself that then shoot out and explore the next solar system. So starting with one probe, you get 1,000. From 1,000 probes, you get 1,000,000, then 1 billion, 1 trillion, 1 quintillion, and before you know it, in just a few generations, you have trillions of these probes expanding in a sphere near the speed of light. Now, you may say to yourself, well, this is too fantastic. I mean, how's that possible? Well, in some sense, it happens in your body practically every day. When a virus lands on your cell, it hijacks the reproductive mechanism of your cell, creating scores of other viruses, which then go out and colonize other cells. So starting with one cell, you get a few hundred, then a few thousand, a few million, a few billion, and within about 2 weeks, you're sneezing. Think about that. One molecule. One molecule makes you sneeze in 2 weeks. And so that's the power of an exponential growth, and that's the basis of the movie 2001. Now, remember in the movie that there was a probe left on the moon, and its duty was to interfere with human evolution and then to send a signal back to the home planet, announcing the fact that we humans have finally arrived, that we are capable of space travel. So I think that's perhaps one of the most authentic encounters with a civilization in outer space. Well, let's move right on to the next listener phone call.
Dr. Kaku, do you believe in any of the ancient alien theories, and what do you think of the new video that surfaced this week showing the 2 fighter pilots, I believe, looking at that object that was just released by the government? My name is Andres, and I am calling from Seattle, Washington. Thank you.
Okay, well, first of all, the History Channel has a series called Ancient Aliens. I've been on Ancient Aliens a few times. And we scientists analyzing these hieroglyphics and these pictures of what looks like alien creatures visiting our ancestors, we say that, well, A, we have to be open to the possibility that they really are visitations from ancient aliens, but B, ultimately we want proof. That is, we want things that are testable, falsifiable, and reproducible. So in other words, when you see an ancient figure that seems to be wearing a headdress that looks like a helmet, and it seems as if they have a spacesuit, well, it could also be simply a ceremonial gown worn by the king to commemorate a victory over an enemy. And so it's not definitive proof. So again, A, we have to be open to all sorts of crazy ideas, because who knows, some of these crazy ideas may be correct. But B, ultimately, we want to have proof. We want to have more than simply hearsay and drawings. Now, some scientists say that why not look for the leftover garbage from ancient aliens? That is, if the aliens created a base, let's say in Latin America, there should be wire, there should be garbage, Coke bottles left over from these aliens, tools, all sorts of stuff that they discarded, because we do the same thing. When we went to the moon, we left our garbage on the moon. And so if these aliens land on the Earth, we should be able to find evidence of that. However, so far, no one has ever picked up an alien screwdriver or an alien piece of garbage from one of these sites. But like I said, we keep an open mind. Now, you also mentioned the fact that up till 2012, the United States Air Force did, in fact, record all sorts of strange phenomenon, 95% of which can be dismissed as natural phenomenon, but the last 5%, as I mentioned, well, they make your skin crawl. They seem to indicate that there is a technology out there far more advanced than what we're accustomed to seeing. What is it? Well, my own personal point of view is maybe, just maybe, these are hypersonic drones being tested by the military in Area 51. That would explain why the fact that they can zigzag without crushing the pilots inside, that they can zoom at hypersonic velocities faster than the supersonic velocities of our pilots, and they are drones. They don't have to have pilots that will be subjected to G-forces and be crushed by all the maneuvers of these devices. Or, hey, maybe they really are aliens from outer space. I'm a scientist. Until I see definitive, hardcore proof, evidence of these things, I cannot say that this is evidence of visitation. But was it a good thing to spend $22 million of taxpayers' money on this project? Many scientists say no, it was not worth it. I disagree. My attitude is, you never know. Perhaps we have been visited. Perhaps there are aliens from outer space coming by and interacting with humans. It's something that cannot be dismissed. But the debate will go on for decades into the future until someone can come up with hard proof. Okay, well, moving right along, let's take the next listener phone call.
Hello, this is G. Paul Hudak calling from Tempe, Arizona. I have two questions, actually, that I'd love to ask. One, is it even scientifically possible to detect distant magnetic fields around exoplanets 100 or 1,000 light years away? And two, do you think that planet Earth would be habitable were it not for the existence of the moon? And actually, now that I bring it up, I'm wondering about your stance on whether or not Earth and Moon are a twin planet system, whether or not we're sort of a dual planet system. Thanks so much. Enjoy your work, and look forward to seeing you again soon.
Well, you asked some very interesting questions. First of all, yes, the Earth has a magnetic field, and it's very important because that magnetic field shields us against the solar wind. If we lose our magnetic field, the solar wind would then hit our atmosphere and literally blow our atmosphere into outer space over millions of years, and we would choke. We would lose our atmosphere, like what happened to Mars. Mars is a frozen desert. It's desolate, but why? It's because it has no magnetic field to speak of. As a consequence, the solar wind hits Mars and blows whatever atmosphere it has into outer space, and that's why the atmospheric density of Mars is 1%, just 1% that of the Earth. Now you ask another question, what about planets orbiting other stars, extrasolar planets? Believe it or not, we have now observed 4,000, count them, 4,000 planets orbiting other star systems in our Milky Way galaxy. But can we detect their magnetic field? And the short answer is no. Our instruments are simply not sensitive enough to give us a detailed look at their magnetic field, which would be important for them to preserve an atmosphere. So what we do instead is we're trying to use spectroscopes in order to tell whether or not there's traces of water and oxygen on these planets. So far, yes, we have found evidence that some of these planets seem to have oxygen or at least water in their atmosphere, meaning that they probably do have a magnetic field which protects them against the solar wind. Also about the moon, you realize that yes, without the moon, the Earth would wobble and eventually flip over, making life impossible. We are blessed with a large moon. The fact that the moon is large means that it stabilizes the Earth's orbit. Realize that we have Newton's laws of motion so accurate that we can actually fast forward the solar system millions and millions of years into the future. And when we do that, we find out that the slightest little perturbation, the slightest wobbling of the Earth is magnified over time until the Earth flips over, which would be horrific for Earthlings. So thank God we have a large moon that stabilizes the Earth. Okay, let's move right along now to the next listener phone call.
Hi, this is Kyle Newman. I live down in Houston, Texas. And I guess my question would be, at what point or what technology or method would we either in the future or currently possess could be used to test for evidence of God or the lack thereof God? And, you know, if it doesn't exist, like in the future, would there be something hypothetical that you could probably imagine that we could use? And what evidence would be able to satisfy the question of God existing or not? And how would we go about getting that evidence?
Well, you ask an interesting question. Actually, I was in Mexico City a few years ago. I was moderating a debate. On one side of the debate, we had Catholic theologians that certainly believed in the existence of God. On the other half, we had atheists, scientists who were also atheists saying, bah, humbug, there's no such thing as God. And there they were, two sides of this debate. And I was in the middle. And, of course, at the end of the debate, they asked me what my position was on the existence of God. Can God's existence be measured? And my answer was very simple, that the existence or non-existence of God is not provable. That is, science is based on things that are testable, falsifiable, and reproducible, and there is no experiment. There is no experiment that allows you to definitively say one way or the other whether there is a God. In other words, 1,000 years from now, we're going to have the same debate. Perhaps 1,000 years from now in Mexico City, another debate will be organized, and we're going to be debating the same question because it is untestable.